Yeah, good morning, everybody. I'm Julien Lefebvre from Aix-Marseille University, and I have the pleasure to present you this joint work with Justine Fraisse and David Germano, two medical doctors in Paris Hospital and Neurospin Center. And it's about the Fiedler vector and quite amazing behavior that this classical characteristic has, and I try to explain some theoretical results about it. So first, some definitions. So we consider a graph with n vertices and edges. This is an undirected graph, so we have the adjacency matrix A, so with entries 0 or 1, depending whether two nodes are linked or not. And there is the classical graph Laplacian matrix that is defined as the difference between the diagonal matrix D here, composed by the degrees of the nodes of the graph and the adjacency matrix. So this matrix is symmetric, semi-definite, positive, and it has n eigenvalues. The first eigenvalue is 0, and the associated eigenvector corresponds to the constant vectors. It's classical. The multiplicity of 0 corresponds to the number of connected components of the graph. Just to have visual intuitions, the Fiedler vector is like this. So the color corresponds to, here in blue, to negative values, in yellow to positive values. And this is a very classical example here where you have two communities, two complete graphs related by a few links. So we clearly observe a sign change in this Fiedler vector. So it allows classical applications in terms of clustering, spectral clustering. So you consider the sign of the Fiedler vector, and you're able to retrieve the two communities in this graph. This is very classical. There is an intuition of that if you know that the first non-trivial eigenvalue here, lambda 2, is associated to the Courant min-max principle. So the Fiedler vector is the minimal vector satisfying those constraints and the minimum of this quadratic form. Okay, so there has been a lot of empirical applications in medical imaging. I won't cite all of them, but for instance, it has been used to parameterize shapes. So for instance, here on the left, you have mandible shapes here. And the Fiedler vector in color here is something that describes the elongation of the shape. In this application, it has been used to register different mandible shapes based on the skeleton of the shape that has been built from the Fiedler vector. I will use something quite similar at the end of the talk in terms of applications. And there has been another application in my team here to parameterize some brain structures. Here, this is the central sulcus. This is a fold of the brain. And by using the Fiedler vector, it's possible to describe this elongated shape and to characterize the folding of this shape by, let's say, with a convenient way. So empirically, this is an interesting feature, but we have not a lot of theoretical results behind. For instance, why is it describing quite perfectly elongated shape? So is it possible to formalize it a bit more? So it has been proposed, this conjecture has been proposed by Chung more than 10 years ago. This conjecture tries to formalize this notion of elongation. So you consider P min and P max, the two extremal points of the Fiedler vector. Okay, so in the previous case, it corresponds to that point and that point. And this conjecture tells you that the geodesic distance between any points on the surface or on the graph is always bounded by the distance between the two extremal points. So, said differently, the two extremal points are on the diameter of the shape. And there is a nice link, but I have no time to explain it, maybe in the questions. So this conjecture is related to a famous conjecture, the hotspot conjecture, proposed 50 years ago, and it's quite funny because a lot of people have worked on it, in particular Terence Tao, and a few results have been obtained for this conjecture. So it has really a mathematical motivation behind. There are counterexamples to Chung conjecture, for instance, with this class of graphs where you have a line graph and a star graph that is glued to this path graph. And when the number here of branches of the stars is quite large, so the conjecture is no more true. So you have an extremum at one boundary of the graph and another one, let's say on the other branch of the star. And there have been other recent results in that direction to generalize a bit more this conjecture, but it's not. There are not a lot of results. So in this talk, I will talk about my contributions in terms of to try to better understand the properties of the extreme values of Fiedler vector, and for that we have used stability analysis of graphs with local perturbations. I will explain after. And I will also show two applications for very different sort of contexts. So first, I define here the perturbations I will use. So a scheme is better than mathematical explanation. So just consider a graph and consider any vertex on this graph, not necessarily the extrema of the Fiedler vector. And the perturbation is just adding a new vertex here, n plus 1, and a weight on this edge. Okay, so you have now a weighted graph. It's possible to redefine the graph Laplacian with weights. It's not a big issue. And just an example with the line graph here with the Laplacian matrix. You have quite easy calculations that gives you the Fiedler vector. This is a cosine function. And if you add a perturbation on this line graph, so just adding this x weight at one boundary of the graph, and if you make vary this perturbation, you will observe this behavior. So in blue, you have the Fiedler vector with a small perturbation. So it's almost constant on the line, and there is a huge extrema at the new vertex. And if you increase x toward infinity, you retrieve the cosine shape of the Fiedler vector. Okay. So it's just the first intuition we can have with a very simple example. Another example here with a graph, the Fiedler vector on the left, and here this is just a perturbation on one vertex that has no particular properties. So on the right, you will see different the evolution of the perturbation on the x-axis. The red curve here corresponds to the value of the perturbed vertex, and in black this corresponds to the extrema of the Fiedler vector on the left. So I will vary the amount of the perturbation. Okay, so nothing happens on the graph in the middle, but suddenly we'll observe a sort of transition here, and just at this moment here where the curves cross, so there are two extrema here, two maxima here, and when the perturbation goes to infinity, you retrieve visually the Fiedler vector. So there is really a change in the behavior of the Fiedler vector, and this is something we can formalize with a proposition that I will explain here. The idea is that it's possible to find a maximal perturbation where the maximum of the Fiedler vector of the perturbed graph is located on the new vertex here. So this is formalized here. Oops, sorry. So here this is the definition of the perturbed graph, so it's like I presented before. And here this is the proposition. You have the perturbed Fiedler vector depending on x. And if you consider this set, so the interval between 0 and a, where the Fiedler vector has its maximum at the new vertex n plus 1, then this set is non-empty, and you can define the sup of this set. Okay, so I have no time to present the proof. It's based on some ingredients such as the Weil's inequalities when you perturbate the spectrum of matrices. So I skip the proof, no time for it. And just I want to insist on that, this conjecture, that when you consider when you add a vertex to the extrema of the Fiedler vector, then for any perturbations, in particular when x tends to infinity, the Fiedler vector has still an extremum at this new vertex. And there is something quite intuitive behind, but with all the classical tools, it's really difficult to find a proof. So would be very happy if someone in the audience has the answer for that, and I will pay him or her a beer. Application 1. So given the previous proposition, it's possible to define a new metric for graphs, for networks. And this metric is based on the previous set I defined here. And we consider the inverse of the sup of this set. Okay, so when you have the threshold where the Fiedler vector of the perturbed graph has no more its extremum on the new vertex, you take the inverse of this threshold, and it provides you a Fiedler centrality. And why? It's also because if the previous conjecture is true, it means that for an extremum of the Fiedler vector, this Fiedler centrality vanishes. Okay, and we can illustrate this centrality and compare it with other classical metric like betweenness, closeness, and eigenvector centrality. The notion of centrality intuitively is typically the number of geodesic paths that goes through a vertex, and if there are a lot of geodesic paths going through this, going through a node of the graph, so there is a large centrality. So here this is an example with a random graph where you can observe the Fiedler centrality. It's quite comparable to other kinds of centralities. Here this is the correlation, it's quite good. But for other instances of random graphs, it's not so clear. Here it decreases, and in that case it's even completely decorrelated. So there is something quite strange. But in general, let's say when you simulate a lot of random graphs, in that case this is with the Erdős-Rényi model, with n vertices and m edges that are fixed, the correlations between the centrality metrics is relatively close to 1, but for some instances it can be decorrelated. It's also possible to vary the number of edges in the random graphs, so going from sparse to dense graphs, and compute the correlations with the Fiedler metric in bold with all the other centrality metrics. Okay, there is a regime of for the number of edges where it's comparable, but for, let's say, denser graphs, it's difficult it's more difficult to find similarities. So at the moment we have no explanation for this result, and I will say a few words about that at the end. And the last application, it's about shape parameterization. So we consider here corpus callosum shapes. So this is a structure of the brain in the middle of the brain a structure where white matter fibers joining the two hemispheres of the brain are passing through. And so this structure is interesting for, let's say, in different pathologies because the shapes is affected. And for my colleagues, it was important to determine the thickness of this shape, so to have a thickness profile, so going from one extremity onto the other, and to compute the thickness of this shape. So a natural solution for that is to have the Fiedler vector and to look at the level set of the Fiedler vector and compute the thickness on each level set. And you can get this sort of map here. In red, this is thick, and in blue, it's thin. But there are some, let's say, cases of shapes where the extremity is not exactly where the neurologists want it to be. So here, it's the extremity of the Fiedler vector is here, and they want something there. So a natural application of the previous results is to perturbate here this graph, okay, and to get a new Fiedler vector that follows exactly the elongation of the shape as the neurologist wants. And in that case, it's possible to obtain thickness profiles, so it looks like something like this. In red, this is the thickness profile of this shape. In bold black, this is the thickness profile of the perturbed corpus callosum. So it's interesting here because the thickness is comparable at this extremity, okay? Whereas in the first case, you had a very different thickness, and it was probably not the good approach. So my colleagues were happy with that, and we are publishing something more extensive to a larger cohort with interesting results. So now, just to conclude, or to say a few words of critical discussions, if you want to reproduce what is present here, the codes are on GitHub. We can wonder whether it's interesting to have yet another metric for networks, because there exist tons of metrics like this. And in general, it's very costful to compute. And in my case, this metric is between quadratic and cubic. And so it's clearly not scalable. And yeah, it's an open question. Is it interesting to use this metric? And in particular, we have not let's say, all the properties to explain the behavior of this metric. So, and an important point to me, this is this is not really related to this work, but there is a responsibility issue when proposing new methods, let's say. It's important that those methods are not used for bad applications, let's say. And I want to do some advertisement for colleagues that have proposed a prototype of license. So Alexandre Monin and Eric Tanier in INRIA, they have proposed this usage right license, and I have used this license for this work and for the code. So if you want to use this work, you have to comply with policies regarding ecological redirections. So I think this is a very interesting initiative, and if you are interested by this, you can look at the webpage of Eric Tanier, and thank you for your attention.
Thank you very much for this interesting talk. Have you got some questions?
Thanks. Thank you for the presentation. So I don't know if I missed maybe something, but I was just curious about like how you construct the graph, getting the shape, like, because of course there are many solutions to do so, and it can influence then the result that you get, right?
Absolutely. Typically for the corpus callosum, yeah. So you can have a mesh of this shape. It's let's say one good solution. In that case, it's not. It's something more brutal, or let's say behind there is an MRI image, and I've simply used, let's say, a for neighbor connectivity, something like this. So it's not completely satisfactory mathematically, but it's something I'd like to work on it to make it more robust. In particular, if you want to take into account the let's say the boundary conditions, the Neumann boundary conditions behind the Laplace-Beltrami things, eigenproblem, it's important to have something